In this video, we continue our discussion on concepts related to gases. And in this section, we're going to discuss the ideal gas law and how that combines all of the previous gas laws we discussed in our last video. And we will look at the kinetic molecular theory of gases, which is a model to describe gas behavior. First, we can take all the laws, Gay-Lussac's law, Avogadro's law, Charles' law, Boyle's law, and combine them together. And if we combine all those relations together, we can produce something called the ideal gas law, or the ideal gas relation. And this is shown at the top. It tells us that pressure times volume is equal to the number of moles times a constant of proportionality times the temperature. And the red asterisks indicate that this is an equation you should remember, simply because of its universality and its importance. It's a fairly easy relation to remember, and it's one from which you can derive all the other relations that we've discussed thus far. If we take a gas at STP, as we saw in our last video, it occupies 22.4 liters, and from that we can take pressure times volume, that is PV, divide by N times T, that is the number of moles, and the temperature. And if we plug in all those values, we get the universal gas constant. And in units of liters and atmospheres and Kelvin and moles, it is approximately 0.0821. There are more significant figures, but to three significant figures, it's 0.0821. If we use different units, so if we use bar, if we use pascals, depending on the unit system we use, R will have a different value. And so you don't need to memorize the values for R. We will give those to you on a table on the exam, and you'll be able to have those available to you as you need them. But you should be comfortable using the ideal gas relation, because that's the thing that you're going to need to be able to do. You may come across 0.0821 enough times that you'll remember 0.0821 liter atmosphere per Kelvin mole. But that'll be provided for you. One side point, when we get on to chapter 6, we're going to see R pop up again. But now we're not looking at gases. We'll be looking at R from the point of view of reactions in solution. So when we do thermodynamics, you'll see that we'll have units of joules per Kelvin mole. And typically for joules per Kelvin mole, the value for R is 8.3. What this shows us is joule is an energy unit, and liter atmospheres turns out to be an energy unit. Atmosphere is force per unit area. Liters is a volume, so atmosphere times liters gives you force times distance. Force times distance is energy. So liter atmosphere is an energy unit, and we'll see this come up again later in our study, so it might be worthwhile to remember that. Another important relation, rather than memorizing Boyle's and Charles and Gay-Lussac's and Avogadro's law, you can simply write down the combined gas relation. So up above we saw PV over NT equals R, and R is a constant. Therefore, if we carry a system from one state, state 1, to a second condition, state 2, we could write out the following equation at the bottom here. Pressure 1 times volume 1 divided by numbers of moles 1 times temperature 1 would be equal to, under the second set of conditions, pressure 2 times volume 2 times number of moles 2 times temperature 2. Whatever units would be held constant would be canceled out. So for example, under constant amount of gas and temperature, we have P1V1 equals P2V2, which is our first relation that we looked at. That's Boyle's law. And you can do that for any of the other laws. So P1V1 over N1T1 equal P2V2 over N2T2. This combined relation can be used to derive any of the gas laws that we've come across. And that's an easy way for you to handle gas problems. With the ideal gas law, we can derive a gas density. We saw this somewhat in we alluded to it in our last video. So the density of a gas it's going to be mass per unit volume, right? And so with the ideal gas law, we can pull out mass from our moles, and volume will come out from the remainder of the equation. So if we write density as mass per unit volume, we know moles is m over mass over the molar mass for the system. So then we can rewrite the ideal gas law as PV equals mass divided by molar mass times RT. And from this, we could derive a density as well. We can see that density is mass per unit volume. We rearrange the equation above, and we end up with molar mass times pressure divided by RT gives us density. And we had a sense of density from our earlier video. If we think, to compare, for example, nitrogen, which has a molar mass of 28 for N2, versus helium, which is 4, we expect the density of nitrogen gas to be 7 times that of the density of helium, because the gas properties only depend on the molar mass, or the number of moles in a system. So we can see the molar mass can be derived from the ideal gas law as well. This is not an equation you necessarily need to remember. You could derive this if you needed to, but it's just an entertaining expression that shows that molecular weights can be derived from gas relations, and just like we derived molecular weights from chemical reactions earlier. So that shows the tie between gas laws and chemical reactions. When we have mixtures of gases, they behave quite simply. Gases mix homogeneously in any proportions. So unlike oil and vinegar, where we get a phase separation, or any of a variety of other liquids, gases mix nicely and uniformly. And then each gas behaves as if it's the only gas present. So each gas will exert what we call a partial pressure. For example, if I have 1 mole of helium gas in a 22.4 liter container at standard temperature and pressure, we'll see that it'll exert 1 atmosphere of pressure, as we know. If I have another container that has nitrogen doing the same thing, it'll exert 1 atmosphere of pressure. If I can combine both of those gases into a single container that has a volume of 22.4 liters, the total pressure will be twice that. It will be 2 atmospheres. Each individual gas, the helium and the nitrogen, will exert 1 atmosphere of pressure. Dalton's law of partial pressure states this, that the total pressure in a mixture of gases is the sum of the partial pressures of the component or individual gases. And the partial pressure can be written down as shown in the equations below. The pressure of gas A would be equal to the mole fraction, that is X sub A, of gas A, multiplied by the total pressure. And the mole fraction is simply the number of moles of a given constituent divided by the total number of moles in that system. We can take our ideal gas relation and now tie that into some of our flowcharts that we had in Chapter 3 relating to stoichiometry. So this is where the complexity begins to build. We can take the 2 green boxes, amount of gas A and amount of gas B, and if there's a chemical reaction going on, those two would be related by some stoichiometry in a balanced chemical reaction. But if they're both gases, we can use the ideal gas relation to calculate under constant temperature, for example, either their pressures or their volumes, depending on which of the other parameters is fixed. So for example, under constant pressure and temperature, the volume of gas A would be related to the ideal gas law, and that could be tied to the moles of gas A, which would lead to the moles of gas B after a reaction, which could lead back to the volume occupied by gas B. So this is a useful and worthwhile flowchart to remember, and we'll do some practice problems with this in your ALEKS homework, in recitation, and in our mechanics videos. We now move on to the kinetic molecular theory of gases, which is a model to describe gas behavior based on the existence of atoms and molecules. The basic postulates of the kinetic molecular theory of gases are shown here. Postulate 1 states that gas particles are very tiny particles with large spaces between them. The volume in a gas is so large compared to the individual particles that the individual particles are treated as having zero volume. So we can state that the volume of each particle is so small compared to the total volume, which is mostly empty space, that the volume of the gas particles themselves can be treated as approximately zero. The second postulate is that gas particles are in constant random straight line motion, except when they collide with each other or the container walls, in which case they bounce out of line and bounce into a different direction. So the gas particles are just balls that move in straight line motion, and gravity does not have any significant effect on them at room temperature and pressure. Postulate 3 are that the collisions are elastic, meaning that the colliding particles will exchange energy but don't lose energy due to friction. So collisions can be elastic or inelastic. Let's think about this. So Six Flags St. Louis used to have a ride, it was bumper cars, and everybody would, a whole group of people, 20 different cars would get together in these bumper cars and drive around, and you'd bang into one another and bounce off in all sorts of different directions. There was a big rubber bumper around each car, and so the cars would undergo elastic collisions, like rubber balls. Sadly, Six Flags got rid of that ride. Then there are inelastic collisions. So I've been driving down the road and had someone drive into the rear end of my car and smash my bumper. That is an inelastic collision. The energy in that collision was converted to energy to destroy my bumper. So for gas molecules, the collisions are elastic. Their total kinetic energy is constant. Between collisions, the particles don't influence each other by attractive or repulsive forces, and they simply bounce off of one another elastically. Here is a graph of the speeds of molecules as a function of temperature. So what we have on each graph is a population distribution, the relative number of molecules in a sample with a particular speed versus the speed. So we can take our first graph, and that's the blue graph, the tallest graph there, and that's at 273 Kelvin, which would be at the freezing point of water. So we're at 0 Celsius. You can see that there's a distribution of speeds. No molecules have zero speed. Small population are slow. But on average, most of them are around 600 meters per second. And then there's a tail going up to high speed. There's a few molecules at very high speed, but then they undergo collisions and exchange. And then slower ones speed up and faster ones slow down. But on average, they maintain the same speed. So this is an equilibrium distribution. If we increase the temperature up to 1000 Celsius, that is 1273 Kelvin, we get the orange curve. You can see that the distribution is shifted upward, where the most probable speed has now gone up to nearly 1000 meters a second, and there are some molecules that are going well over 2000 meters per second. And if we heat up to 2273 Kelvin, we get the red curve, and you can see that the most probable velocity gets up near 1500 meters per second, and there are molecules that are traveling nearly 3000 meters a second. The take-home message from this graph is that for a given system, as we increase the temperature, the speed, particularly the most probable speed, but Also, the average speed increases. The average speed increases with increasing temperature. Here we see that as the molecules move with high speeds, they can collide with the wall containers. And just like if you were to go into your room and slam yourself into the wall, you would see the wall move and there would be a sound on the other side. So you're imparting energy. Hopefully you don't break through the wall and mess up your drywall, but there's clearly energy imparted. And for a typical container, these collisions, multiple collisions with gas molecules create pressure, and they create force against the walls. We can use this kinetic molecular theory now to rationalize the various gas laws that we've looked at. So let's take a look at Boyle's law. So we have a system where the temperature and the number of moles is a constant. So we're looking at the relationship between pressure and volume. So for a given pressure, a gas will have a given volume. If we double the pressure, the gas gets squeezed down. And then the system equilibrates at a new volume. So P1 V1 will equal P2 V2. If P doubles, V goes in half. Why does the volume decrease? Well, we need more collisions to counterbalance this external force. The more collisions there are, the higher the pressure of the gas inside. At a smaller volume, there'll be more collisions of the gas with the size of the container. The pressure will go up. We can look at Dalton's law of partial pressures. Each individual gas will exert pressure. If you put both gases together, each one will still continue undergoing collisions with the walls. Therefore, the pressure now will be the sum of the pressures exerted by each individual gas in the mixture. We look at Charles' law next. So here we see we have a gas at temperature 1. The pressure of the gas equals the atmospheric pressure. Now Charles' law is going to relate temperature and volume. So in this case, our number of moles will be fixed and our pressure will be fixed. So if we take a sample of gas and we heat the gas up, if temperature goes up, the collisions will be with higher velocity, more forceful, and we will create higher pressure. Therefore, the volume of the system will increase until the internal pressure equilibrates with the external pressure, and now we'll end up with a new volume at the same pressure we started with. Therefore, we'll have a larger volume. So at higher temperature, we need a larger volume because each collision will be more forceful. Next, we can look at this kinetic molecular theory of gas volume of Avogadro's law. If we increase the amount of gas, we increase the collisions. Therefore, the volume of the gas must increase to equilibrate with the background pressure. So, as we increase the amount of gas, we increase the volume of the gas. Now we're going to go back to a statement we made way back in the first chapter. We talked about the types of energy, and we had two types of energy. If you recall, there was potential energy and there was kinetic energy. We made the statement at the time that kinetic energy was related to the speed of molecules, and here we see that that's what we have. At a given temperature, all the gases in a sample have the same average kinetic energy, regardless of their composition. So, for example, if I have a mixture of nitrogen and oxygen, nitrogen has a molar mass of 28 grams per mole, oxygen has a molar mass of 32 grams per mole. Even though they have different masses and different chemical compositions, At a given temperature, all the molecules have the same average kinetic energy. So that is, the nitrogen molecules have the same average kinetic energy as the oxygen molecules. And the energy is equal to 1/2 the mass of the molecule times its speed squared. So we see the kinetic energy depends both on the mass and the speed of the particle. That's basic expression, Newton's relation for kinetic energy. Kinetic energy is 1/2 mv squared. So at the same temperature, a heavier gas particle is going to move more slowly than the light particles. This graph illustrates this. We have a plot of our molecular distribution of speeds, like we looked at earlier for nitrogen. So we have the relative number of molecules at a given speed versus the speed. These are all gases at the same temperature, but they have different molar masses. We have oxygen, nitrogen, water vapor, helium, and hydrogen gas. And you see, of course, that hydrogen gas is by far the smallest molecule at 2 grams per mole, and it's got a much higher speed than all the others. We could relate the speeds through the 1/2 mv squared relationship. This leads us to Graham's law of effusion. Effusion can be visualized as following. Imagine you have 2 containers that are attached to one another. One container has a gas, and the other container is empty. It's been pumped out with a vacuum pump. Now, if we open a small hole between the 2 chambers, gas can leak from one side into the other side. So gas will escape from the high pressure region to the low pressure region. Effusion is this process by which the gas escapes through the small hole in its container into an evacuated space. So it just randomly moves until it finds the hole and out it goes. Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. And we would recognize this from what we just learned. For a given temperature, the kinetic energies are going to be the same. So molecules with higher mass have lower velocity. They'll move slower. They'll get out the hole more slowly. The lighter gas moves faster and therefore gets out of the hole faster. And the rate of effusion then is proportional to 1 over the square root of the molar mass of the gas. We'll do problems with this later on. Here you can see effusion illustrated by black and red particles. The black particles are lighter and they escape faster. The final relation we can look at is something called diffusion. Diffusion is very similar to effusion because it's related to the square root of the molar mass of the gas. But diffusion is where 2 gases intermingle with one another. And a way to think about this is an experience that one of our chemistry faculty had a number of years ago, back before the time of social distancing. We were in a lecture hall, and a student at the back of the room in a large lecture hall had a container with pepper spray to drive away attackers, and it was in her purse, and somehow the top of the pepper spray container broke off, and it began releasing a nasty gas. And of course, those who were nearby immediately began coughing, and then the wave of coughing moved to the next row and the next row, and it worked its way through the class as the gas diffused through the atmospheric gases until it reached the instructor, at which point he said, "We need to end class now," and everyone rapidly exited the lecture hall. One gas was diffusing through the other gas. That ends our discussion of these basic gas relations and kinetic molecular theory of gases. And we'll continue on with real gases in our next video.